This video is on radiation and the greenhouse effect. Question 1. State the law of conservation of energy. Energy cannot be created or destroyed. Energy can only be transferred from one form to another. The total energy in the universe is constant. Question 2. Define absorb, reflect, and emit. So absorb means to take in without reflection. Reflect means to give back from a surface. And emit means to release. Question 3. State the definition, equation, and units for emissivity. What is the emissivity of a really dark colored object? What is the emissivity of a really light colored object? Emissivity is a measure of how well an object emits or radiates electromagnetic waves. Little e equals emissivity, which is power radiated per unit area divided by sigma t to the fourth. Has no units. So sigma is a constant. For a really dark colored object, the emissivity is close to 1. For a really light colored object, the emissivity is close to 0. The emissivity of a black body is 1. The emissivity of a star is about 1. Do not confuse emissivity E with efficiency E or the exponential function E. Question 4. State the definition, equation, and units for albedo. What is the albedo of a really dark colored object? What is the albedo of a really light colored object? Albedo is a ratio of light reflected to that received. It's like whiteness. So albedo is equal to the Greek letter alpha. It's total scattered power divided by total incident power. Has no units. So the albedo of a really light colored object is close to 1. The albedo of a really dark colored object is close to 0. And the albedo of a star is about 0. The Earth's albedo is about 0.315. And it varies daily and is dependent on cloud formations and latitude. Question 5. What is a mathematical relationship between the albedo and emissivity of an object? For non-transparent opaque objects, we have the following relationship. Albedo plus emissivity equals 1. But do not always use this equation. Maybe you should never use it. Just remember that the albedo of an object is inversely proportional to its emissivity. Question 6. Define black body. A black body is a perfect absorber and emitter of heat. Question 7. A naked person has a surface area of 1.8 meters squared, an emissivity of 0.980, and a skin temperature of 37 degrees Celsius. This naked person is in a room with room temperature of 20 degrees Celsius. How much energy does this person lose per minute? So we have this equation. Emissivity equals power radiated per unit area. So power per unit area, and then I multiplied both sides by sigma t to the fourth. Then I multiplied both sides by area. Power is energy over time. Then I multiplied both sides by time. We know energy is P delta T. So this is going to be E sigma A T to the fourth of a black body minus E sigma A T to the fourth at room temperature. So E sigma A gets factored out. T to the fourth of a black body minus T to the fourth at room temperature. There should be a fourth power here. Question 8. By which factor does the power emitted by an object decrease when its temperature decreases from 800 Kelvin to 500 Kelvin? So we have this equation, E sigma T final to the fourth divided by E sigma T initial to the fourth. The E sigmas cancel out. Question 9. On a hot summer day, a forest receives an intensity of approximately 1,210 watts per meter squared. If the forest has an albedo of approximately 0.122, then determine how much energy absorbed and reflected every second by each square meter. So this is the amount absorbed here. As you can see, this is 1 minus albedo. So that's the amount absorbed. And this is the amount reflected here. Question 10. The planet Saturn has an average surface temperature of minus 178 degrees Celsius and a radius of approximately 5.82 times 10 to the 7 meters. Suppose Saturn has an emissivity of approximately 0.650. Determine the rate of thermal energy emitted. So the rate of thermal energy emitted means power, because that's energy over time. When you see that word rate, that's something over time, most of the time. So we're solving for P. They gave us E, sigma is a constant, T to the fourth, they gave us T. And this A is a surface area, which is 4 pi r squared, which is the surface area of a sphere. Question 11. Define luminosity L. Units. Luminosity L is the amount of energy a star emits from its surface per second. This is an intrinsic property of a star. The units of luminosity L is joules per second or watts. For a star or a black body, luminosity is sigma A T to the fourth. So if you let luminosity equal power per unit area, that's power per unit area equals sigma A T to the fourth, which is exactly this equation here, except we're letting E equal 1. Question 12. What does the Stefan-Boltzmann constant tell us? What does the Stefan-Boltzmann law tell us? State the equation and determine and define each variable in the Stefan-Boltzmann law. The Stefan-Boltzmann law tells us the power emitted by an object. So L equals sigma AT to the fourth. L is the luminosity emitted by the object. Sigma is a constant. A is the surface area of the object, and T is the temperature of the object in Kelvin. Question 13. A spherical body of 5 centimeters in diameter is maintained at 700 degrees Celsius. Assuming that it radiates as if it were a black body, at what rate in watts is energy radiated from the sphere? So we're just going to use this equation. Remember, if it's a black body, then E is equal to 1, the emissivity. Question 14. The average surface temperature of the sun is 5.778 times 10 to the third Kelvin, and its average radius is 6.957 times 10 to the 8 meters. Assuming that it radiates as if it were a black body, so little e is equal to 1. At what rate in watts is energy radiated from the sphere? So that P equal E sigma AT to the fourth, but little e is equal to 1. Question 15. The radius of star X is 4 times that of star Y, and its temperature is 3 times that of Y. Find the ratio of luminosity of y to that of x. So the radius is 4 times greater, and its temperature is 3 times greater. So we want L sub y over L sub x. So we know L is sigma AT to the 4th. So we end up getting this fraction. Question 16. A black body has a surface area of 4 meters squared and temperature of 450 K. The black body is in a closed room with room temperature of 293 K. How much energy does the black body lose per minute? So this is sigma AT to the 4th minus sigma AT to the 4th. And remember, E equals P delta T, because P is equal to E over delta T. Question 17. Define apparent brightness B. Units. What is the mathematical relationship between apparent brightness B and luminosity L? Apparent brightness B is how bright a star appears to a detector on Earth. This is not an intrinsic property of a star. Apparent brightness B depends on the distance a star is from a detector and is given by the equation B equals L over 4 pi d squared, where d is a distance from the star to the detector. The units of apparent brightness B is watts per square meter. Question 18. The luminosity of the sun is 3.846 times 10 to the 26 watts, and its distance from the Earth is about 1.5 times 10 to the 11 meters. Determine the apparent brightness B of the sun. So we just use this equation. Sorry, L over 4 pi d squared. Question 19. The apparent brightness of star X as observed from Earth is 3 times greater than that of star Y as observed from Earth. The luminosity of star X is 2 times greater than that of star Y. Determine the ratio of the distance of star Y to Earth to that of star X to Earth. So we have these two equations for the brightness, for X and for Y. So now just divide the two. So we end up getting b sub x over b sub y is equal to this function. Then let's solve for d sub y over d sub x. We end up getting this. And it says here the apparent brightness of x is 3 times that of y. So that's why b sub x here is equal to 3b sub y. And the luminosity of x is 2 times greater. So luminosity of x here is 2 times greater than that of y. So here's our solution here. Question 20. What does Wien's displacement law tell us? State the equation and define each variable for Wien's displacement law. Draw and label a graph describing Wien's displacement law. So Wien's displacement law tells us the maximum wavelength of an electromagnetic wave, which is emitted from a black body. So this is the equation. Sigma max times temperature equals 2.9 times 10 to the minus 3 meters times Kelvin. These are the meanings of both variables. So let's just assume this red curve has a temperature of 1000 Kelvin meaning you have a sphere, it's a black body, it has a temperature of 1000 Kelvin. This orange is 2000 Kelvin, the yellow is 3000 Kelvin, the green is 4000 Kelvin, the blue is 5000 Kelvin. As the temperature of the black body increases, the amount of intensity radiated outwards increases, and the wavelength, the maximum wavelength, decreases. So if the maximum wavelength decreases, then the frequency increases. So maybe you're asking yourself, what's the meaning of wavelength and frequency? You'll learn more about that when we learn about waves, hopefully. This is important here. As the temperature of the black body increases, the maximum emitted wavelength decreases, and the maximum emitted frequency increases. Question 21. The sun emits electromagnetic waves with the maximum wavelength of 570 nanometers. According to this information, what is the surface temperature of the sun? So we're just going to use this equation, solve for temperature. Question 22. The maximum surface temperature of the red Jupiter Giant Betelgeuse is approximately 3.8 times 10 to the 3 Kelvin. Determine the maximum wavelength emitted. So use the same equation, solve for lambda. Question 23. What is the meaning of the Sun-Earth solar constant? The solar constant is the average intensity the top of the Earth's atmosphere receives from the sun. Question 24. The luminosity of the sun is approximately 3.828 times 10 to the 26 watts. The average distance from the sun to Earth is 1.5 times 10 to the 11 meters. Use the equation I equals P over A, which is equal to P over 4 pi d squared to determine the Sun-Earth solar constant. So this ends up becoming pretty close to 1400 watts per meter squared. So the solar constant is about 1400 watts per meter squared for rounding to 3 significant digits. Question 25. Take a look at this image. Describe the equation average intensity equals P over A equals S over 4. The area of a two-dimensional circle is given by the equation pi r squared. The surface area of a three-dimensional sphere is given by the equation 4 pi r squared. The approximate average intensity of electromagnetic waves reaching the Earth from the sun is given by the two-dimensional area of the Earth divided by the three-dimensional surface area of the Earth. So if the sun emits electromagnetic waves, the amount of waves that pass this two-dimensional circle is pi r squared. So then we have to average that out over the whole Earth, which has a surface area of 4 pi r squared. So pi r squared divided by 4 pi r squared is equal to 1 over 4, or the solar constant over 4. Question 26. The average albedo of Earth is approximately 0.3 and the average emissivity of the Earth is approximately 0.6. Use the solar constant to determine the average temperature of the Earth. So, the left-hand side tells us the thermal energy received by the Earth. So the left-hand side tells us these arrows here that pass, or that are about to pass, this two-dimensional pi r squared surface area. So it's going to be alpha times the solar constant times A cross-sectional. That's this here. Equals the thermal energy emitted by Earth in the same time interval. So the thermal energy emitted by Earth is this, E sigma AT to the fourth. And A is 4 pi r squared. So we end up getting about 16 degrees Celsius. Question 27. The average albedo of Earth is approximately 0.3. Use a solar constant to determine the average intensity reaching the Earth during the day or night. So let's memorize this equation. Plugging everything in, we get about 237 watts per meter squared. Question 28. Define the greenhouse effect and the enhanced greenhouse effect. What are the four major greenhouse gases? State their name and chemical formula. So, the greenhouse effect tells us that the Earth's atmosphere keeps the planet warmer than it would be without the atmosphere. This is essential for life on Earth. The enhanced greenhouse effect, also called anthropogenic climate change, tells us that the Earth is radiating and reflecting electromagnetic waves at a lower rate than it is receiving it because of human activity, which means the Earth is getting hotter. Electromagnetic waves travel from the sun and reach the surface of the Earth. The electromagnetic waves are reflected from the surface of the Earth. Some of those electromagnetic waves are absorbed in a greenhouse gas. Some of those electromagnetic waves in the greenhouse gas are then emitted back to the surface of the Earth as opposed to space. This means that the Earth is getting hotter. So these are the four major greenhouse gases: water vapor, carbon dioxide, methane, nitrous oxide. These four greenhouse gases are also necessary for life on Earth. So understand the absorption of infrared radiation by the main greenhouse gases in terms of the in terms of the molecular energy levels. Okay. So do browse these websites for more information on climate change. And do explain what went wrong from these climate predictions.